My name is Samuel Schmidtko. I'm presenting our work on differentiable plasticity done at the U.S. Naval Research Lab with my amazing colleagues Joe Hayes, Julie Ashkenazi, and Ed Lawson. And real quick, I just want to share a TLDR for the presentation, which is we're taking synaptic plasticity rules from the neuroscience literature, and we're learning their parameters through gradient descent. Okay. So to begin, we're just going to jump right into the technical details before we discuss the results. For this work, we use the spike response model presented in the Slayer paper. And the spike response model is a generalization of the leaky integrating fire neuron model, which instead of being formulated as a set of differential equations, the SRM is formulated using filters. So for example, in the first equation, the spike response kernel, the epsilon there, is convolved over the spikes from the previous layer to produce a current, and the current is weighted by the synaptic weights and summed with the somatic refractory response kernel, which is in the second equation there, that V. And this is this postsynaptic potential is used to go through a spiking function, and that produces the spikes. But as many of you know, backpropagated gradients do not naturally have the ability to go through the spike function, which is why we have a lot of great local learning rules such as EPROP and the local learning rules that are presented to get through this. But another way of doing this is to do a surrogate gradient. And that's exactly what Slayer does, is they present a surrogate gradient, which basically is a gradient approximation for the spike function, and it allows you to backpropagate through this non-differentiable function, and that's what we use in our work. So in modifying the SRM equation, we add both a set of fixed weights, like from the previous set of slides, and a synaptic trace, along with a learning rate for that trace. You can see that in the second equation there, we have the plasticity coefficient alpha, and then the synaptic trace E. And the dynamics of the synaptic trace define plasticity in the network and follow a generalized structure demonstrated by the bottom equation. And this is ultimately a function of local parameters and function activity. And we discovered that by utilizing this ability that Slayer provides for backpropagating errors through the SNN, we can learn the quantities for local parameters governing the dynamics of synaptic plasticity rules through gradient descent. So those are what we differentiate through. So 3 plasticity rules are taken from the neuroscience literature and explored in this work. The first of these rules is the linear decay rule, which is at the top there. It's a simple Hebbian rule that sums the joint pre- and post-synaptic activity at the weights. We also use Oja's rule, which is a modification of the linear decay rule that overcomes the inherent unbounded weight growth and naturally computes a principal component of the network activity. So it gives interesting dynamics. And finally, we look at the BCM rule, which is based on a theory describing the synaptic development of neurons in the visual cortex. LTP and LTD are defined by a sliding threshold. And yeah, these are the 3 rules we use. The blue circles you see demonstrate the local parameters, which are learned through backpropagation. In the linear decay and Oja's rule, only the learning rates of the plasticity dynamics are learned. However, the BCM rule, both the learning rates and the learned LTP and LTD threshold for the rule is learned. So that's the initial threshold that is used at the initial time step of the process.
Samuel, I just want to give a quick 2-minute warning. You may want to move through some of this a little bit quicker.
Okay. So we also show that in this work, the neuromodulatory signals that act to modulate the dynamics of plasticity rules can be learned jointly with the plasticity rules themselves. The neuromodulatory dynamics can act identically across all neurons or can be learned to be neuron specific. These rules are generated by an independent network, but can also be computed by the network itself. And here's some of the results. So the first experiment in this work was taken from the EPROP paper and is inspired by rodent learning experiments in neuroscience. Basically, a series of sensory cues are presented. Either they go on the left or the right, and the network must determine which side had more cues and must make a decision to go left or right after the long waiting period. We show with the graph on the left that spiky neural networks without plasticity are unable to hold information in memory long enough to solve this task. However, the differentiable plastic neural networks are able to solve this task with relatively few gradient steps. And by adding significant noise to the experiment, it doesn't degrade training significantly. And on this next task, we do a robotic locomotion problem where we maximize velocity in the x direction. As you can see on the bottom right training curves, plasticity does not improve the training performance. However, in the presence of noise, plastic neural networks demonstrate significantly more stable performance despite this source of noise not being trained on during the training phase. Specifically, as you can see there, the plastic networks are robust to joint noise and action output noise, but surprisingly, they're not robust to observation noise. And this was all not seen during the training phase, so it was a surprising outcome. Okay, you said I had 2 minutes left?
Yeah, unfortunately, we are getting kind of crunched here at the end, so we probably need to transition if you want to maybe take 30 seconds to wrap up.
Okay, I was just going to share some ongoing work, but I'll just run through that really quick. We're now working on some STDP learning rules. We're doing a pair-based, triplet-based, voltage-based, and we're observing the dynamics of all that. We're looking at adapting to limb damage type problems, and we've demonstrated thus far that training in a zero-shot setting, plasticity models can improve adaptivity to limb damage even without any learning signals. And this is only further improved by the addition of neuromodulatory signals. Okay, that's it.
Great, thank you. Yes, just because we are sort of running behind schedule, I think maybe we will do questions for these last two talks in the chat, but I do want to remind everyone there is a working group tomorrow at the same time on continual learning. I think that would be a fantastic place for discussion and more questions on these topics. But with that, I'll hand over our remaining minutes to Jack.
Thank you.